So now we'll talk about Adadelta, which avoids setting an initial learning rate completely, right? So let's see what it does. So I have some n epochs or n iterations. So I have computing the gradient. Then I keep exponentially moving history Vt, okay. Then I do compute the update, right? So this is what my update is going to be, right? And that update is a ratio of two variables. One is ut. I have not defined what ut is yet, but it's ratio of ut and vt. Of course, the square root is there, but there is no eta naught here, right? So we still need to see what is ut and how does this ratio take care of the challenges that I was talking about. Yeah, so let's see. So ut, then I update wt because I've computed the delta which needs to be there, right? So that's this is simply yeah. So this part is simply equivalent to, I mean, the equivalent of minus eta naught divided by square root of eta into del wt, which I had in the previous algorithm, and then my update rule was wt minus this, right? So this is my delta, and then my update rule is just going to be wt plus delta. So that negative sign has been taken care of inside, and I don't have the initial learning rate. Instead, I have this in the numerator, right? So all of this is making sense. And this is what my ut is, right? So my ut is an accumulation of the updates that I have made. So remember, this is nabla wt square. I am representing the gradient as nabla wt. Right, so derivative is nabla wt and the update is delta wt, right? So this is what this is keeping track of the deltas, and my current derivatives are nablas, right? So I have like two histories being tracked, and then I'm taking a ratio of these histories and then adjusting the learning rate. How does it solve my problem is still not clear, but right now we are just trying to understand what the equations are, right? So instead of one history which was vt, I have two histories now. It's also clear that one history is kind of ahead of the other history, right? So vt was tracking everything that is happening up to this time step, but ut is also tracking what has happened at this time step, because it's also taking into account the current update which has been made, okay. So these two changes are, these two ratios are being, these two histories are being tracked, and then I'm taking a ratio of these two histories, and that is my effective learning rate. So how does this help is the question, okay. Yeah, so ut will only be used in the next iteration. That's what I meant by that one history is running ahead the other history. Vt is already used in the current iteration, but the ut that I have computed now will be used in the next iteration as ut minus 1, right? So the numerator is one step behind the denominator, okay. Yeah, so now the numerator is a function of the history as opposed to being a constant in RMS prop and ADA. So we have made it a function of the history, we have got rid of the initial learning rate, but does it really solve our problem is the question, right? And the other thing to note, which will be important in understanding that it indeed solves our problem, is that whatever derivative we have computed here, whatever derivative we had computed, we are already taking only a fraction of that in Vt, right? And even the update that we have, right, we are only taking a fraction of that when we are looking at ut. Okay, this is something important to note. Why and how this makes a difference is something that we will see, but the main thing to note is that we are only taking a fraction of the update that we have made, and this update that we had made was a function of this delta wt that we had, right, the gradient that we had, okay. So don't worry, we will just clear these things in the next couple of slides. Yeah, so now suppose you are in a high curvature region, right? So you are in a steep region, and what do you want in the steep region? You want the effective learning rate to be small, okay. So at time step 0, your v0, so you can refer to the equations here, the equations for vt, ut and all of that. I'll just not bother too much about referring to them again and again, but these computations are according to these equations, right? So at any point you're confused, you can just pause and verify that we have used the same equations, right? So v0 is going to be 0.1 into delta w0 squares. then you will have the, nabla W0 square, where nabla W0 is the derivative. Then you have the update, which is the delta W0, the change that you're going to make in W0. And currently your U minus 1 is 0, right? So then you only have epsilon in the numerator, U minus 1 is going to be 0. So you make that update. Then you do W1 is equal to W0 plus delta W0. Then you compute U0, right? And this is what I was emphasizing on, right? That this U0 is just taking a fraction of the derivative that you had, right? And now, U0 was actually beta times the old history, which is 0 in this case, and 1 minus beta time the current update that we have made. But the current update, which is delta, is in turn a function of this nabla. So I've just substituted the value of delta W0 and in terms of delta W0 in terms of nabla W0, right? So this is nabla, just in case you're confused, and this is delta. Okay, so that's done. Okay, now let's see what happens next. I'll just keep continuing for a while. So fraction of the history is being stored for the next iteration. Now at t equal to 1, again you will just apply this v1 is equal to 0.9 into the previous history plus 0.1 into the current gradient, and if I substitute the value of the previous history, then I get the entire equation in terms of the nablas, so nabla W0 square and nabla W1 square, right? Now I again do the update, and now I am ignoring the epsilon because I have reached a state where I have non-zero U0s and epsilon is very small, so U0 plus epsilon is going to be very close to U0 anyways, right? So this is what the update is. I make this update and then I compute U1, right? And again U1 is a function of deltas, remember, but the deltas in terms are functions of the nablas. So I just put those values appropriately and I have computed this, right? And now if you look at this, right, so, or maybe let me just go to one more time step, t equal to 2. Again, I'm doing the same thing, as I'm just mechanically substituting values into the formula and just making sure that I express everything in terms of delta Wi's, right? That's the only idea, so that all the formulae become comparable, right? All the values become comparable. So this is where I am. Now I'm just going to focus on the U's and the V's, okay? So now if you look at this time step, right? So when I was here at t equal to 2 time step, I will use U1 divided by V2, right? So this is my U1 and this is my V2, and you can compare these two equations and you will know that U1 is actually smaller than V2, right? So if U1 is smaller than V2, then the numerator is smaller than the denominator, and hence the effective learning rate would be small, and hence my problem has been taken care of, right? In the steep region, I am having a smaller denominator, a smaller effective learning rate, right? That's exactly what I wanted. And the entire picture will become clear also when I talk about what happens in the flat regions, right? So that's also something which is coming. So let's wait for that to happen. So both Vt and Ut are increasing, right? Because both are accumulating gradients, but because of this one time step delay between them, right? One is Ut minus 1, the other is Vt. So in the steep regions, while both are growing, Ut is growing slightly slower than Vt, and hence the effective learning rate is going to be smaller, right? Now, yeah, that's all being same here. Whereas in the RMS prob, the effective learning rate would just have been eta by Vt, and hence there is no adaptation happening here, right? Okay, so this is all that I've already said. You could just read what is on the slides. Now let's see what happens in the flat regions. Okay, so now I'm in the flat region. So this is some delta Wi, right? At the ith time step, I am trying to take the gradient. Now what will happen here, right? So now if I look at Ut minus 1 and Vt, okay? Now Ut minus 1, remember, is one time step behind Vt. So then one way of looking at it is that in Ut minus 1, these all are participating, right? And in Vt minus Vt, these all are participating, because by this point the beta raised to k is so small that that guy is effectively not participating, right? Because there's this one time step difference. So this is what the situation is. Now what is happening if you look at this curve, right? So since all the gradients were high, 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 and then they started decreasing, my UT, since it's looking at more high guys than the low guys, right? So because of this one time, so VT has this current guy also, which is again very small, right? And UT does not have this guy. It has some other guy which was actually high, right? Because it's one time step behind. So now UT is going to be larger than VT. Does that make sense? Because VT is one step higher. So once you enter the steep regions, after a while, because this new guy is getting more weightage in VT, that sum would start becoming smaller as compared to UT, because UT still has to come to that step. It's still in the older history, and the older history was all high gradients. So it's still taking more benefit from the older history, whereas VT is now relying more on the current guy. And this current guy will affect UT minus 1 only in the next time step, right? So now the history, the UT minus 1 is going to be larger than VT, and hence the ratio is going to be larger, and hence the effective learning rate is increasing as you are entering the flat regions, right? And then you can continue arguing that once again, if you enter the steep region, again because of this one time step delay, what will happen is VT will start looking at a much bigger gradient than what UT is looking at, right? So UT might be looking at these guys, whereas UT minus 1 would be looking at, UT minus 1 might be looking at these guys, whereas VT will start looking at the current gradient also, and this is a very large value. So it has more benefit from the current large value, and hence it would be larger than UT minus 1, and hence the effective learning rate will again decrease, right? So that's what is happening here. Okay, so that's the explanation of why having this two histories, one delayed by one time step, is helping, because it allows you to catch up with what is happening in the history and then update the gradients accordingly, right? So these values are not important, but as long as you have understood the pictorial explanation, you will be able to relate it to what is happening with these values, right? So therefore, Adadelta allows the numerator to increase or decrease based on the current and past gradients, and that's exactly what we wanted. Now let's see what happens if we run Adadelta. So as usual, RMS prop is oscillating. Adagrad is taking more time to reach the minima because it aggressively kills the learning rate, whereas adaptive delta, let's just look at it again, right? So yeah, so in the steep regions, as it became steeper, it's decreased, and then it did whatever was required to reach the minima quickly, right? Where the other two algorithms are struggling, one is oscillating while the other one is slow, right? Yeah. Okay. Yeah, now let's look at, we are also plotting now the VT and the UT, right? So because they are delayed by one time step, their curvature would be the same, right? They would have the same shape. So both of them have the same shape, but their magnitudes are different, right? Because of this delay, one is relying on more on the past history, like one more time step from the past history, whereas the other one is relying more on the current history. So what is happening is that when you are entering this, let's see. So what is happening is in this curve, so what happened was initially you were in a high loss region, right, or a high loss region, but also a relatively flatter region, right? Here the difference between the contour lines is higher than what happens as you keep going down towards the valley, right? So that means initially your gradients were small, right? So the guy who is going to be behind, which is UT minus 1, is going to look at smaller gradients, whereas the guy who is ahead is started looking at faster gradients, higher gradients, right? So that's why what is happening is that the magnitude of VT is large here and the magnitude of UT is small here, because UT is still looking at the flat history, whereas VT is one step ahead, so it has looked at more steeper history than what UT minus 1 is looking at, right? Therefore, VT is larger than UT, and since we were going in a steep direction all the way around, this is a favorable situation to have, right? We want VT to be larger than UT so that effectively the ratio is small and the learning rate is accordingly smaller, right? So that's exactly what we wanted, and that is what is happening. Now I can show you this more clearly on the next slide, where if you look at the learning rates for Adadelta and RMS prop, then RMS prop, it constantly decreases, right? Because it does not have any adaptive nature, as it it has to keep decreasing because it's 1 over the accumulated history in this case, and since the history was always steep, whereas in Adadelta you see some kind of adaptation happening, and overall Adadelta is able to converge faster on the plot that we had seen. Yeah, so let's look at some of these values also. So here we had set the initial learning rate to 0.013. So this curve is 0.013 divided by the square root of whatever, and this both started at 0.20, right? That's the what the initial value was, but this only decreased up to 0.12, and hence it was able to kind of converge faster, whereas this was 0.05, and then it became so it decayed more as compared to what Adadelta decayed, right? So this is what has happened here. Yeah, and this is especially important because in the flat regions, we did see a slight bump in the learning rate, right? So it's not like monotonically decreasing, but in the once it reaches a bit closer to the no, it's still decreasing only, right? Yeah, sorry, that's not correct. Yeah, yeah. So that's how the two decays happened. Okay. So this is what the effective learning rates are looking like, and now let's see how the algorithm proceeds. So as you can say that Adadelta has already converged because it was not aggressively decaying the learning rate. It had a reasonably high learning rate which allowed it to converge. RMS prop is slowly getting there because it has aggressively decreased the learning rate, right? And now maybe the usual problem of oscillations may be there or maybe not. I think the figure has ended, so I don't know. The animation has ended, so I don't know. But the main thing is the difference between these two plots, which is explained by these two plots. These are the same two plots drawn on the same scale, right? So now I have drawn both the plots on the same scale here. And in the case of Adadelta, it was not decaying aggressively, whereas in this case, it was decaying aggressively. Okay. Yeah, so that's what we have already gone through. Now let's put all the algorithms together on one plot and see how they behave. So the same loss function, same starting point, and we have these different algorithms right from gradient descent all the way up to Adadelta. And Adadelta is the only one which has this adaptive learning rate in the sense of not having an initial learning rate, right? So let's see. And you see the expected behaviors, right? Okay, let's see, let it stabilize and we'll comment on it. Yeah. Yeah, so you see all of it, all the behaviors that we expected. The black curve is gradient descent, which is slowly moving. We know that does not have any momentum, does not have any adaptation. The momentum and the Nesterov have the usual effect of oscillations, and Nesterov you can again see slightly better at dealing with the oscillations, but all three of them have a problem in moving in the W direction because W was relatively sparser. So they first try to move in the B direction and then come back, whereas Adagrad, RMS prop and Adadelta, they all start moving in W and B direction, and of these Adadelta converged the faster because it was able to adjust the learning rate. RMS prop as usual had the oscillation problem, right? So all of these effects you may again wish to watch this a few times, just play the video when you go to the slides and just make sure you notice all the behaviors that you are familiar with. Okay. Yeah. So we'll end this here.